Good morning, or good afternoon, or good evening, depending on when you're connecting in from. Thank you for taking time out of your busy schedule to come listen to a joint webinar between us and one of our top tier partners, Renaissance. Today's topic, of course, is unlocking the secrets of creating unforgettable embedded products. So whether it's the hardware you choose or the UI you build combined, making the right choices can really help you have your product stand apart from those that you may be faced with in competition. So if this is your first time connecting to one of our webinars, if you're having any audio issues, please check your audio settings on your PC or try refreshing your screen because we are broadcasting over the internet. And of course, whatever's going on the internet that day may interrupt the packets that are coming to you. Of course, we do have all the speakers here to address whatever questions you may have about their topics, and we will address those questions at the end. So please use the Q&A or the chat window to submit your questions to us. And of course, if you haven't followed us on any of our social feeds, we're active on LinkedIn, Facebook, as well as Instagram. You can follow us using the hashtags GUI Development, of course, or Crank Amatech. So today we're lucky enough to have from Renaissance TJ Mueller, who is the business development manager for both the MPU and the MCU side of things over there, as well as Gary Clarkson, who's one of our senior solution architects here at Crank. And of course, there's me, Scott, who is the product marketing manager for our UI development tool, Storyboard. So what are we going to talk about today? Well, first of all, we're going to jump into an introduction into Renaissance hardware, discussing all the great things about the MCU and MPU hardware they have to offer. And then we're going to jump into how they deliver outstanding performance and superior graphics and AI vision capabilities. And then I will give you a quick introduction as to who Crank Software is and, of course, what our GUI development tool is, Storyboard is. And then I'll also discuss in there why the UI is a critical part of the overall development process, and really more importantly, part of the product that you're developing. And then we'll see how all that kind of comes together with a demo of Storyboard and deployment onto the target system. And of course, we'll address your questions at the end. And with that being said, I'm going to hand things over to TJ, who's going to kick things off and talking about all the great things that Renaissance has to offer. TJ.
Okay, thanks again, Scott. And I'm TJ Mueller with Renesas. I'm responsible for business development for Renesas's embedded products, which include our microcontrollers and microprocessors. Let's talk a little bit about the agenda for the Renesas here. So we are going to be introducing our portfolio of embedded processors, including microcontrollers and microprocessors. We'll start off with the RA8 or RA microcontrollers and focusing on the RA8D1, and we'll have a demo of that, of Storyboard running that. Then we'll move on to the RZ microprocessors, and we'll talk about several products there, the RZ-G2L and G2LC, and then RZ-V2L and RZ-V2H. But first, let's talk a little about the Renesas product portfolio, a rather broad portfolio that has really gotten bigger over time. On the left side, we have analog and power, so PMICs and clocks essentially there. In the center, we have sensors, RF, and some optical. And finally, on the right, we have the embedded products, which include microcontrollers and MPUs. And we're focusing today on the red boxes, the RA series of 32-bit microcontrollers and the RZ series of 32 and 64-bit high-end microprocessors. So let's talk first about the RA family of 32-bit microcontrollers. There's 4 series in this, the RA2, 4, 6, and 8. Pretty easy. And we offer up to 480 megahertz, and using the M85 core with the RA8 series. We also offer up to 2 megabytes of embedded flash, We have a host of security features, including Trust Zone, broad connectivity and graphics, and robust cap touch interfaces. And finally, it's a very scalable product family, from 16 pin to 224 pin, 48 megahertz to 480 megahertz. Okay. Let's talk specifically about RA8 here. So we currently offer three series in this family, three members in this series. Sorry, we start off with the RA8 M1. This is our mainstream, focusing on the performance, security, and low power. And then moving into the center one there in the red box, we have the RA8 D1, which is our focus today. And this is, display/graphics focused products, looking at industrial HMI applications, security panels, patient monitoring, so on and so forth. And we also have the RA8 T1 series, which is focused on motor control and for industrial and advanced industrial applications. So let's talk about a little bit more in depth about the RA8 D1. It's again graphics focused. It's got we're the first to have offer the ARM's Cortex M85 core with AI ML capabilities, 6.39 core marks per megahertz. We have advanced graphic peripherals for high resolution displays, and supporting a strong ecosystem of partners for the graphics and the Vision AI. Advanced security features, including hardware root of trust, advanced cryptography, and ARM's Trust Zone. Also, these devices are very low power consumption, and we also, so very low power consumption and various operating voltages, and ease of development with comprehensive software and tools. We have our FSP flexible software package supporting RTOS and open architecture, and a robust partner ecosystem like we have here with Crank. RZ family of 64-bit MPUs. Let's talk about these now. So we switched from our microcontrollers to our microprocessor. The microprocessor family is called the RZ family, and there's 5 series within this family. On the upper left, we have the RZV for Vision AI. So these products are focused on those applications. We have the RZN and RZT focused on the industrial networking, real-time control, so a lot of motor control and applications like that. Going down to the bottom left, we have RZG, which is our general purpose and graphics focused, supporting Linux and Android operating systems. And finally, we have the RZA, which is an RTOS-based microprocessor. So that supports only 2D graphics. Let's talk a little bit in depth about RZG and RZV series of MPUs. Starting off with RZG2L and G2LC, they're like brothers here, if you will. So these devices both feature dual Cortex A55 cores at 1.2 gigahertz. And a subcore for housekeeping activities with an M33 subcore in it. 16-bit interface to DDR3L and DDR4. The camera interface is MIPI CSI or parallel, and display is MIPI DSI or parallel. So some flexibility there. 3D graphics with ARM's Mali G31. H.264 codec on the G2L only. The G2LC does not have that. And in terms of interfaces, we have 2 gigabit Ethernets, 2 CAN FDs, and 8 analog to digital controllers. So some of the benefits are there's a 20% increase in general processing performance from the A55 core versus the A53. and 3 times faster edge AI performance capability with the A55 core. We keep your system safe from security threats with our CIP Linux offering and 10 years of long-term maintenance on that. And we also offer an optimized, Renesas PIMIC to reduce the power supply design complexity. And then finally, the applications are, home appliances, industrial HMI, doorbells and intercoms, and smart cameras. And we have the block diagram on the right, so that's featured in all these slides. Now let's move to the RZ-V2L product. Like the RZ-G2L, it features a dual Cortex A55 core and the same subcore. It differentiates from the G2L in that we have a built-in AI accelerator we call DRP AI, capable of 0.5 TOPS. Same interfaces in terms of DDR, and the graphics and camera interfaces are the same, just a little more detail on the frames per second and the display capabilities. We have a codec. And then a high-speed interface, we have PCI Express, which is different than the G2L, USB 2.0, and 2 GBs. And again, on the last one on the features there, it's pin-to-pin compatible with RZ-G2L. So you could upgrade if there's a need for AI acceleration. Some of the benefits, they're very low AI inferencing power, extending your battery life and, removing the need for a heat sink. Low thermal output, obviously, and, fast time to market utilizing our AI application libraries. Applications here are products that need smart vision AI capability, like trail cameras, video doorbells, monitoring cameras, and security gates. And then finally, our RZ-V2H, which is the latest member of our family here and in full production. This device has a quad-core A55 at 1.8 gigahertz, so it's faster than the V2L. It also features 2 Cortex R8s running at 800 megahertz for motor control applications. And then it also has the M33 subcore for housekeeping. This has the RZ-V2H has an enhanced AI accelerator, DRP AI, capable of 80 sparse tops and 8 dense tops. So this compares to the V2L, which offers a half of a top. So far more robust product here. Another differentiator here for V2H is it has 2 32-bit interfaces to LPDDR4 and then DDR4 and DDR4X at 3.2 gigahertz with inline ECC. It's got the same 3D graphics accelerator for the 4K camera interface. So this is a 4K camera interface here, 30 frames per second. MIPI CSI, MIPI DSI we have as well. H.264 and 265 encoding and decoding for RZ-V2H. High-speed interfaces, PCIe Gen 3 here, 4 lanes, USB 3.2, and again, 2 gigabit Ethernet interfaces. So some of the benefits are we have a high real-time processing capability with these the 2 Cortex R8s, eliminating the need for external microcontrollers, so saving money and all that. Also, again, low AI inferencing power, enabling battery life and smaller footprint. And reduced optical system costs because we have the ISP on chip and enabling multiple camera connections. Applications here are applications which require smart AI, vision AI capability, including service robots, cleaner robots, industrial drones, and factory automation. And of course, we have the block diagram on the right. So that's what I've got here. I'll hand it back to Scott to talk about storyboard.
All right. So, in case you haven't heard of Crank before or even Storyboard before this presentation, I can guarantee you that at some point in time, you probably have used a product running an HMI that was built using our GUI development software, Storyboard. Crank was founded in 2007 by a leadership team with an extensive background in embedded software systems development and graphics. And just to let you know that Crank is both a software and services company, which means that we have our software storyboard as well as validator, as well as if you have the vision of what you want your UI to look like, but maybe you don't have the time or you don't have the in-house resources, our team of professional services can actually create that for you from the ground up. And so Storyboard is our GUI development framework, and it was really created to help make GUI development process more efficient for embedded platforms. So this is just a sample of just some of the customers that have trusted Crank Storyboard or our professional services team to help them develop their products at HMI. So when it comes to developing GUIs for today's embedded products, things have become increasingly more challenging than it was in the past. Definitely, user expectations on what a device with a screen can do, or more importantly, should be able to do, have been greatly elevated by the smartphone. Plus, competition for products has greatly increased. This has resulted maybe in your projects being given shorter development times in order to stay ahead or keep up with the competition, as well as integrating evolutions in technology into your product can impact the longevity of the product, right? So how competitive can it remain, and how can the product's user interface be leveraged to take full advantage of this has all become a thing. And of course, anytime development time is lost, or maybe development time or the work done is wasted due to coding changes needing to occur, this can all create delays in getting the product to market on time and maybe on budget. So when it comes to creating exceptional user experiences for embedded products, of course, the most important step is getting the most out of your target system's memory and graphical capabilities, therefore making sure its performance is top notch. The great thing about it is that our developers have taken on a large portion of this work for you by creating pre-built and highly optimized runtime engines for each of the hardware and software combinations that we support. So a great example of this is that we support the RA8D1, and we work closely with both the team at Renesas as well as the team at ARM to take full advantage of all the hardware capabilities, plus is ARM's Helium architecture that the folks at Renesas embedded into their structure. So we work by working closely with the hardware vendor. We ensure that we make the most of your hardware's graphical performance and memory resources, so you don't need to waste your valuable time and needing to code, compile, test, and repeating this until it works. Furthermore, we have a variety of embedded tools that Gary will go over shortly to really help ensure that the application is further optimized for the target hardware. So with that being said, what can you do to help ensure your product's GUI provides an exceptional user experience? Well, increasing the glanceability of it is great. So depending on the product you are developing, the screen can greatly range in size. And of course, a smaller screen, while decreasing the bill of materials costs or increasing the portability of the device, can greatly affect the user's ability to access the information, understand the information, or maybe even recall it when time comes. And so the key to exceptional UX or user experience is about making the UI as glanceable as possible. So for example, one of the greatest benefits of today's devices is that they can be connected and provide users with a wealth of information. With a simple glance, we can obtain information that otherwise is only available on PC or smartphones. A great example of that is smartwatches, right? This means that determining what exactly the user needs to see at any given moment on the screen they are interacting with and providing that exactly to them becomes vital. Next is reduce the clutter of the information being shown. So keeping it simple helps users get in quickly in and out of the functions they need to and understand the functions that are being presented to them. This can include everything from text, button sizes, use of menus, the color even, and much, much more. So some tips to help with that include using buttons and swipes. This way, the user is able to gain access to the information they want to and ideally 2 clicks or swipes or less. Scrolling lists really helps reduce the content. So scrolling or wrapped menus can help provide access to loads information, but in a small controlled number of items at a time to help focus the user's attention and declutter the screen. Also, simple typography or simple text type. When it comes to the typeface, a simple font type is one of the most readable options. Find one, stick with it, and ditch the others. Avoid using fonts like serif and script fonts when using a fewer number of pixels to keep things highly tight and legible. Of course, leaving space between elements. This is straightforward, but keep in mind that space can make or break a design on a small screen, right? Too much of it, and you'll run out of room for other content, and too little, well, it makes things seem hard to read and extremely cluttered. This is even more important if you plan on translating for other markets where you may get undesired effects and be forced to redesign the UI completely because of a lack of space for text screens to grow in length. Next up is optimize the GUI app content interactions used in the design. So graphics typically consume the most resources, and planning your pipeline carefully helps to create a sophisticated experience that doesn't glitch or stutter at runtime. So it's important to consider these things when developing your graphics. So for example, image format and loading mechanism can have a big impact on the runtime performance. Encoded formats such as PNG and bitmap really require resources to decode raw file formats are typically pushed directly to display with less overhead. Also, to help minimize rework across different size screens, consider using scalable vector graphics and assets since they are easy to scale. However, it's important to note that they do consume runtime CPU cycles to reside. Having development tools that scale them for you as part of the deployment process is ideal. And also, as mentioned, animations can greatly improve explainability, but they may be confusing to the user if not designed well. So having the ability to create, test, and edit animation sequences within development tools before target deployment can really help streamline that whole process. So also animations can also be processor intensive, especially when trying to create a kind of a smart-like phone experience with smooth screen transitions and drop-down menus. So using performance tools really helps optimize animation overhead, and it's a good idea to baseline CPU and memory utilization right from the beginning of development. Also, consider using hardware acceleration where available to offload the CPU from performing the high-running graphic tasks. Another thing to do is maybe think about alternatives to animations. So, some of the things that we've done before is using kind of flipbook style animations to really kind of, provide that high scale animation feel, but with less overhead and less intensive processing power. Also, with differences in access time between memory types, it's generally a good idea to maybe store the dynamic content in RAM, such as the image frame buffer, and persistent data in Flash, such as the application code. And this will really kind of help things as well. And of course, when it comes down to it, test some more, and of course, test again. I know it goes without saying that testing is an important part of the process. However, the user interface represents the customer's main interaction point with your product. But all too often, it is maybe the core functionality that the user interface drives and receives all the testing attention. So remember, test drive the user interface. Testing the user interface in the development phase allows the functionality from a user's perspective. So GUI testing ensures the performance and functionality accuracy of the application's visual elements. It tests graphical icons, visual indicators, and the user interface elements like buttons, text, boxes, menus, and more. This validation is carried out through the various test cases and scripts, either manually or with the help of automation tools like maybe Jenkins. And, to help really catch bugs at an early stage, resulting in an improved user experience. Also, it helps capture unintended user interface changes. So, in order to ensure that an application is consistently providing the experience that is intended for the user and the UI has not taken any unexpected turns. And of course, finally, a great UI design is a process. It's inevitable that design changes are going to occur at some time. So, it's important to bake that time into the development process for these to occur and embrace them rather than fretting about them at any point during the development time. So, with the product's user interface and user experience becoming one of the main factors that it's being measured upon, and is driving the value that users of the product see in the product, what are some key tips on UI, UX? Well, like I said, simplicity and usability. A product's ease of use and simple information presentation are vital determinants of the product's relevance. UI and UX design play a pivotal role in really ensuring a product offers solutions to a user's problems, and most importantly, provides an exciting and hassle-free experience. Also, accessibility and availability. No doubt that the technology has shaped the world and provided tools to encourage ease of living. As an advantage to businesses, UI and UX design elements are one out of a million technological transformations existing to create roadmaps of a product's development, making products obtainable to users by understanding individual needs and wants, thus becoming a prerequisite, a request, becoming a requirement for product marketing positioning. Also, responsiveness and correctness. A product's function to swiftly respond to a user's commands is critical. Hence, the importance of UX design and providing users with quick and seamless navigation while interacting with a product. And then, of course, customer-centric design. It's pertinent to note that UI and UX design elements are solely responsible for compelling a user to make decisions to embrace a product's offering and values. Without the required UI and UX design elements, with the user as a center of attraction or attention, a product can really quickly lose its relevance and positioning to the target market. So, what are the results of a good UX design? Well, research shows that on average, every dollar invested in UX brings about $100 in return. The best design performers increase their revenue and shareholders' returns at nearly twice the rate of the industry counterparts. And that 8 and 10 out of 10 customers are willing to pay more for a better user experience. Therefore, your product's UI UX can really make or break the success of your product. And this is where Crank Storyboard can help with your product development. So, Storyboard was created to help remove the inefficiencies and hurdles that often plagued software developers when it came to developing UIs for embedded devices, such as having to code every rectangle, circle, or square from scratch, or having to wait for others upstream or downstream to complete the work before beginning theirs. And even the introduction of last-minute design changes requiring the recoding of the UI application. And this is because Storyboard offers a distinct separation of design and code environments, with the front-end design being decoupled from the back-end logic, enabling developers and designers to update and test the app at the same time in parallel without destroying or delaying each other's work. This makes it a purpose-built for collaboration, developing of GUI applications. Within its framework, developers and designers can work on their part and iterate with ease in the quest for developing the optimal end user experience without needing to wait. Also, its unique rapid design iteration and re-import technology enables designers or developers to import and re-import design files from popular design tools such as Photoshop, Sketch, and Figma, with all the action or events that were previously established, the previously already kind of created within the application, being reattached to the changed ones. And also, it provides hardware and OS independence. So Storyboard really enables cross-platform development, so that way GUIs developed for one hardware can be easily deployed on another one simply by using the appropriate runtimes providing project portability, therefore really enabling you to switch from MPUs to MCUs, or in the case of Renaissance hardware, maybe from the RZG to the RZV hardware, or maybe from the RZG to the RA8D1. So, but how exactly does Storyboard's decoupled architecture enable you to create UI applications quicker and more efficiently? Well, it does in three different main ways. One, Storyboard's development architecture makes it easy to get started early on the GUI development, easily embracing design iterations, reducing the complexity of developing GUI applications, resulting in faster time to market for products. So, as previously mentioned, UI development can begin within familiar UI design tools, and when they're ready, can be easily imported into Storyboard, creating the building blocks of the UI application. From there, UIs can be brought to life using Storyboard's integrated animation tool, allowing you to create, edit, and review animations all directly within the Storyboard IDE workspace. Actions, events, and screens transitions can easily be added via drop-down lists, reducing the need to code everything from scratch. As well as critical UI flow and usability testing can be performed within Storyboard using its integrated prototype and simulation functionality called Validator. Also, even as development cycles begin to wind down, designers and developers can easily continue to fine-tune the UI based on feedback or required market changes without impacting the progress that was already made, i.e., causing a complete teardown of code. This allows you to completely modify the UI application look. It's as simple as re-importing the changed design files into Storyboard, all without having to create an entirely new application or overriding the previous work that was done, such as, like I mentioned, adding the action, events, screen transitions, etc. So you can remain in control of the iteration of these design iterations through our unique graphical compare and merge tool, through which you can choose which change content you wish to accept and deploy into the UI before committing those changes to the final design. This really makes it a more efficient process when maybe working in a larger team. Also, Storyboard provides developers with actionable insight to assist with development decisions as the UI is being developed. Through its performance and optimization tools, you can monitor the resources directly within Storyboard, so you know with confidence that your UI can be optimized or is bestly optimized for your target hardware's memory and resources. And like I said, it provides you with UI flexibility. So even with the vast choice of hardware and operating systems that you may need or come across, it's highly likely that Storyboard UIs can run on it. So Storyboard was really created to be platform agnostic, so that way you can help de-risk your embedded device project by introducing a framework that easily supports technology and design changes at any point in the development cycle, allowing for a broad range of UI flexibility such as scalability, so being able to scale up to powerful MPUs or maybe scale it down to small footprint MCUs. It also allows you portability, so making switches to your technology stack, whether it's hardware or software, to take advantage of specific board features or capabilities, like, for example, the new RZ V ones that TJ was talking about. And of course, reusability. So your GUI apps can be used across different product lines, really providing you for a consistent brand look, touch, and feel, simply by reusing the UI from an older project for your new one. And then also, just to kind of quickly touch upon this, really to help ensure embedded GUI applications work as intended, Storyboard Validator can be added to your Storyboard IDE. So integrated within Storyboard's development workspace, you can add the validator as an add-on option, which really helps streamline the overall GUI development process by making the whole testing process a more intrinsic part of the development process. So test cases, developer one can be used across projects and platforms of another, really saving you valuable time and effort when testing new features or enhancements that are made to the embedded GUI application. Also, test reports can be generated and shared with the project team, keeping everyone informed on the status of development. And of course, it can be integrated into a Jenkins environment so that systems run tests independently or more regularly without the need for manual triggers or interventions. And so with that being said, I'm going to pass things over to Gary, who's going to actually talk about storyboard a little bit more in depth and actually give you a quick demo. Gary?
So yes, thank you, Scott. The way that storyboard is used is quite different to other tools and approaches. So I'm going to take one or two slides to give you a kind of a high level overview of why we do things the way we do, and especially why we're slightly different to other solutions. And we think actually much better, and that's why storyboard was created in the first place. So Scott talked a lot about parallel development and iteration. So storyboard is all about iteration and really looking at the process, the flow of creating a user interface and trying to make the hard things easy. It's one of our aims as developers of the product, is to look at all of the things that are really quite difficult in UI design and remove the blockers. And as part of this, the whole idea is to run in parallel. So we have tools that your designers, your design team, your industrial capability people, the people really with all the talent and UI UX experience. As a software engineer myself, my UIs are actually pretty terrible, and software guys make terrible UIs in general. So it's always best to really work with the tools that are designed for creating beautiful user interfaces. And the people with that talent are the ones who can create the look and feel and the user experience. So not only are they able to create the user experience in their own environment, the best tools, things like Photoshop, Sketch, or Figma, they're also able to do some of the prototyping themselves. So we take those device schemas, those layouts, and import those models into storyboard directly. So they're still in charge and engaged in the design process. So we're not requiring the skills of a software engineer really up front to create the layout and the first resolutions of the screens. They can be achieved a lot easier with storyboard by using our tools. So in parallel, the developers are bringing up the platform. They're maybe working on the back-end system, the control aspects of whatever the device is going to be doing. And at some point, the UI and the back-end, we call it the back-end where the state machine is, they'll come together. So they'll bring together, and you're going to be wiring up events and behaviors and messages between the front end, which is the storyboard kind of engine part, and the back end, which is the traditional kind of state machine code that normal software engineers will write. In between those, we have a very flexible framework called Storyboard IO, and Storyboard IO is this. It's an event mechanism, event with payloads if you require, passing backwards and forwards between the front end UI and the back end. And this is how things happen. So a button press on the UI would be passed to the back end as an action to spin a valve or turn a motor or something. And conversely, some data state change in your back end, maybe it's a parameter change or a sensor value increase. This is mapped into an event, and a message is passed from the back end to the front end, and the UI receives that event, and that triggers a UI update. So it's actually very open architecture. It's very simple to implement, and it's very clean. So this abstraction between doing the front end UI, the creative part, and the back end control part are very well abstracted, and we've got tools to simulate and to drive that. So if we look at the architecture of how this all fits together, I'm looking here at the microcontroller architecture, but what I'll also explain as I go along is how this works on something like Linux, a microprocessor environment. So as TJ was saying, the RZ family, the RZV2, etc., runs something like Linux as an operating system. It has a full file system, and we'll be putting files there instead of header files and such, so kind of encoded files in an MCU environment. So a full Linux operating system runs most of the OS for you. We sit on top of that with our layer. So the green stuff in the diagram is the storyboard componentry. So we're sitting on top of the OS, on the top of the file system, on top of the drivers. And we're kind of middleware, really. And essentially, we're an additional task or process. In Linux, it's another process. In an RTOS, it's a single task, alongside whatever else you're doing. And these things are communicating backwards and forwards with these events to make things happen. And alongside that, we have all of the, we call them assets, the graphical components. So images, font files, script files, and such. So these are all making up the entire system. So the architecture is identical from a application development perspective when you're looking at an MCU or an MPU. So with Storyboard, you learn the techniques, you learn the skills and use the same tool. You learn that once, and you can deploy to one or many targets using the same environment. So we use a runtime engine rather than creating code which is compiled. So in this way, and I'll show you a little bit of this later in the presentation, but in this way, we're very flexible about being able to move between targets. And in fact, with the abstraction of the user interface from the actual hardware, many of our customers use Storyboard very early in the design phase to really scope, produce a prototype UI and scope it by deploying it to one or many different targets. So you could, for example, use an RZ V2 or an RZA or an RZE or one of these other platforms, and use the Storyboard engine and the UI prototype to inform your decisions about which platform is the most appropriate. Do you need hardware acceleration, or is software rendering more than adequate? So these sorts of decisions can be done early, and we encourage that as part of the design phase in the specification. So we don't actually talk directly to the hardware. We're sitting on top of the operating system, the drivers. So in terms of integration with the backend system, is pretty straightforward. So today I will be focusing on the new RA8D1, the Cortex M85 EVK. So what I've got here is a small application which is running on there. For an MCU platform, this EK has a 480 by 854 pixel DSI display. So it's quite a large display for an MCU. With display size, the resolution is the most important factor. Resolution to us are pixels. Pixels means memory, and you can have 2 or 4 bytes per pixel. So in terms of looking at your solution architecture, you're specifying your hardware. You can look and see how many pixels are on your display, and you can calculate the frame buffer sizes. And these are often some of the largest factors. So I'll go into in more detail. So I'll show you how we go about design from a step-by-step phase. I will import something from a design tool. In this case, it will be Photoshop. I'll add some simple navigation. I'm not going to be doing a lot of development on the UI. And then I'll step away and show you actually the different application, which is our e-bike demo that we were showing for any of you who were at Embedded World or are going to be at Embedded World in the US. We'll have this on the stand. And we'll show you how we've worked with the ARM guys to integrate the ARM 2D library. So this is the acceleration library from ARM, which leverages the helium vectorization extensions present on the Cortex M85. And we're leveraging that again by using that framework to accelerate some of the drawing operations, blitting, masking, clipping, that sort of thing. And lastly, I'll show you how we actually deploy it. And I'll show you in 2 ways. One will be how you would do this on an RZ platform, so a Linux target with one-click deploy. And on an MCU, it's slightly different. It doesn't traditionally have a file system, so we'll be doing it in a slightly different way. Okay, so I'll quickly show you the screen here. I'm going to jump into the demo with this in a little bit, so I'm not going to spend much time on it, but this will be the demo which I'm going to be deploying and running on the target board. It's an e-bike cluster display. It's a demonstration, of course, but it's quite nice, and it shows some of the useful techniques that you can use to create useful and beautiful UIs with simple implementations. And so there are a few tricks and things I'll point out and things to think about. There's always many different ways to create a user interface. And then lastly, the integration side will be the code and the storyboard libraries integrated with the Renesas framework and also some of the ARM frameworks within the CMSIS environment. In this case, we're using the MDK5, which is the ARM compiler 6. The reason for that at the moment is that this is the best environment, the best tool for leveraging the Cortex M85 vectorization helium instructions. So not surprisingly, the ARM compiler 6 is by far the most optimized for the helium side of things. So there are other solutions, LLVM, and closely following are some implementations with GCC. But as we sit here today, the ARM MDK5 is the one for choice. Okay, so that's what I'll be showing you. So looking at the actual integration, it's very simple. So Storyboard creates a model, and the model runs on our engine. And our engine is a bunch of libraries which are integrated with your application. In architectural terms, Storyboard is one more task on an MCU. So in this case, we're running FreeRTOS, and FreeRTOS will have a task for the Storyboard engine, and it will also have any other tasks that you're running for controlling your state machine or your device or your machine, whatever it's doing. So literally we're adding one or perhaps two tasks. The second task may be something to do with scanning user input from a touchscreen or buttons or rotary encoders. So one more task, in addition to everything else, Storyboard does require a basic real-time operating system. And there's a very good reason for this. Fundamentally, any user interface on any target platform is asynchronous to anything you're doing. The user can interact with the screen at any point. They can touch it, and you don't want to have any lag or any kind of delay between them touching it and something happening. So with the use of an RTOS, you're able to run in parallel to make it asynchronous behavior with whatever tasks. It also simplifies the architecture a lot by not having all of your state machine code in a huge while loop. So essentially, one more task, very simple to do. Load the model, initialize the plugins, and hit run. And the very first thing it does, and this is where the impedance matching comes in. So Storyboard sits on top of the hardware drivers. Obviously, you need to somehow initialize the display on the device. So in this case, the LCD. You need to turn the backlight on. You need to set up the LCD interface. So whatever else you have to do to get the display ready to receive the frame buffer. So this is where the GR generic display init, the kind of init function is called once and only once when we're starting up. So here we're setting everything up. We're telling Storyboard where the buffers are, and we're also doing some things to enable the hardware acceleration and turning the GPUs on and things. So that's done once. And very simply, every time a pixel changes subsequently, another function which you implement, and this is all your code, very simple, is do whatever you need to do to take the frame buffer and copy that to display. So the generic display update is called every time a pixel is changed. Now, we don't update the display every 60 times a second or anything like that. It's an on-demand render engine. So it's only being called when we've created a render surface and decided that there is a pixel changed. And that will update the display when it calls this function. And you can call whatever drivers you need to make that happen. Now, we also support, and this is important on some lower end platforms, not the RA8, because that's pretty high end, but smaller devices, maybe with slower display interfaces, we're able to do what we call damaged rectangle update. So the render engine renders the screen. It'll also tell you the physical coordinates of the bounding box that has changed on that update. So if you've got a slow display interface with a partial frame update capability, you can just send the pixels that have changed. And this is a real performance improvement on many lower end platforms. You're not copying the whole screen every time. So very simple to integrate, very easy to port between platforms. Essentially, this is the same on every platform. Some of the API calls to the hardware and drivers differ between DSI interfaces and parallel LCDs, but essentially the task of integration is very straightforward with Storyboard. Okay, so what I'll do now is I'll quickly switch over to Storyboard tool. So this is our Storyboard Designer, and this is our one and only product that Storyboard that Crank creates. So it's a design environment. It's based on Eclipse, so we leverage the Eclipse environment. And what this means is that if you have your favorite plugins with Eclipse, you know your tools for collaboration, maybe some revision control or Git tools. We're built on the architecture which allows you to pull those in and use them like you would with any Eclipse environment. So it's very easy to integrate with and to integrate into your workflows. So at this stage, we've got a blank screen. Where do you start? So what is the first stage of design? If you have many assets and font files and display wireframes already, you can manually create those. So we have drag and drop capability, and we have lots of primitives like fills, like circles, like arcs. So you can drag those on, create them by hand very quickly. Bit of basically cut and paste development. So what I'll show you now is one of the fast track methods where we're using the iterative development capabilities that Scott was mentioning earlier. So this is where we're bringing the design team into the environment, and they're going to be doing the design up front using, in this case, Photoshop, and I will be importing that into Storyboard. So blank sheet of paper syndrome. Let me show you one of the designs that we've prepared. So this is something that one of our in-house team created. Is a kind of a thermostat example. You can see we've got what we call screens are implemented in Photoshop world as artboards. So an artboard is a screen, and each of these layers, each of these screens has layers, and each of these layers has controls on it. So looking at the thermostat screen here, I can turn off some of the things, and you can see how it's stacked up. So effectively, you're building up the UI like a stack of pancakes. Okay, so background layer, and on top of that becomes things laid on top of that, and on top of that, you've got more stuff on top, and you can see how it's stacked up. And the layers are essential for UI development because they allow you to add overlays and move things around. And the render engines inside of Storyboard take those layers, and we call something called compositing, which is collapsing that stack of pancakes down into a flat image by observing alpha blending and other behaviors. Okay, so this is how it's all put together. Very simple to do. We have some guidelines for this, and so if you are working with any designers, we can give you that PDF. It's 2 or 3 pages. Just some useful tips to make it easy to import. And you can see one of the things is in naming standards. So when you bring this into Storyboard, you're going to be doing some work with it, and you might as well call it something sensible rather than image 1, 2, 3. It's the camera image or security image, for example. Okay, so we have We have screens here. We have these concepts of buttons. We've also got several other screens laid out. You'll see there's a common theme here. And this is another thing in user interfaces. There's often some kind of navigation. So this bottom bar here is a navigation bar. And this is common on every screen. So we're able to use that capability by effectively creating something called a shared layer in Storyboard. And what that means is that we will map all of those different instances down to one. So if you change the menu bar on one screen, it automatically updates and everything. So it's a quality of life improvement. And it also means that you've got consistency across all of your UI. So you don't have to do that, but you know, if it's useful and your UI needs it, then it's a real benefit and much easier to manage and manage change. Okay, so I'm not going to do much more. Hopefully that's a kind of insight into the designer's workspace, and they're using Photoshop or Sketch or Figma to do their design, and they're much more creative. They have lots of tools at their disposal to create beautiful UIs. Okay, so that's day one. The design is maybe finished, and now it's time to bring that into Storyboard, and then we want to build it in such a way to deploy it to the target. So what I can do here is use the features of the imports. So imagine doing this manually. What I can do is pull that in PSD file in. So that's what we were just looking at. I'm going to click this button here, and it's going to deconstruct that UI and then recreate it inside of Storyboard. And imagine doing this manually with moving pixels around, trying to align everything exactly to what the UI designer wanted. But actually, it's done in a matter of seconds. Okay, so I'll zoom out slightly. All of our different screens are here, and here's our thermostat screen. Okay. And I've created what's called a model here, and you can see this layout, this structure is kind of very similar to what the designer created. I'm going to set the thermostat screen as my start screen, and what we can do now is, you know, at this stage I could even click build, and this will create a model, and I could deploy that to the target. Okay. First of all, I'll show you something very quickly. I'm not going to spend much time on this, but very quickly how you can start wiring the UI together. So think about navigation. Okay, so these icons here, these are what we're going to use to move between the screens. So in Storyboard, everything is an action. So I can add an action, and the trigger for that will be, in this case, a press. Okay, so this is a mouse press, and I'm going to do these are lots of different things you can do, kick off animations and such. I'm going to do a screen transition. I'm going to do a screen path, and that one is the icon for the thermostat screen. Okay, I'm going to do one more. I'm going to add the same thing to the weather screen, press screen transition to the weather screen. Okay. So now this is common on all the screens. So if I look at maybe this one, you can see here that I've got the press actions listed. Okay, so that shared layer, that shared navigation thing is going to save me huge amounts of time, even more time than maybe bringing in the individual elements and building it yourself. So what the deconstruction did when I brought it in was create all of the images, you know, basically broken out all of those individual images and icons as individual PNGs, and those are now in our asset family to do things with. Okay, so what I can do, talked about the parallel design, so no code still. I'm going to run this, and I'm going to turn up some tracing, and that's going to start up over here, and now you can see that I've got this screen transition. So with no code at all, I'm able to start prototyping. So that's a pretty retro behavior. I could do much better if I had some talent, but of course I'm a software guy and I don't have talent. So there we go. We've got some behavior, press and release. That's how we do buttons. So we don't use widget frameworks, we use buttons. Buttons are a background image and a foreground image, which we flip between the two. So you can have anything you like. You're not constrained by somebody's idea of what a button looks like. Okay. So we've done some work here. You know, you've done your first version of the UI, and now it's time to deploy it. So those imports are there. Oh, by the way, I could go and re-import a file. This is fairly unique to Storyboard. Not only can you make a design at the first phase, but you can then go and re-import it. So the designer then takes the design, makes some changes to it, moves some colors around or whatever, some adjustments, and they can re-import that or basically reskin that back into the application. And this means that you can carry on your development work, and it will basically replace all the images and remap everything around. So as long as you keep the names the same of the elements that you're using, we map things by name. So it's very simple, very powerful, and it allows you to keep the designer focused on the design phase and keep the software guy kind of working in a parallel way. Okay, so let's look at deploying that now. So I can take my model. Actually, before I do that, I've shown you the what we call the model view here. So the top level is the model. We've also got a resize tool here. So resize allows you to rescale dynamically the screen. Maybe somebody comes along in your team and says, actually, we've decided to use a different resolution display or maybe a different form factor. Our resize tool here can do that automatically for you. So it's a huge improvement over laying pixels out in code. So yes, this model, the platform I brought in is actually just a bunch of fonts, a bunch of images, and some script files. Okay, so when we're deploying the model, which is this GDE file, we're going to create a gap file. And these things are literally copied to the target. So if I show you how to do that, I'm going to take that application, store it as a gap file, and transfer it on SCP. So 10, this is your IP address of the board. I don't actually have an RZ board here, so I'm just showing you in principle. So this would match as long as you have an SCP connection to your Linux target. You'll be able to deploy things with one click. Apps. So I'll show you the runtime aspect in one moment. Okay, so that's where I'm going to put things. I said about our abstraction layer. So from an application looking down, the way you design and develop is platform independent. So whether you're looking at an MCU target or a Linux target, or even a QNX or a Mac target or Windows, from an application looking down, it's the same. From the hardware up, we use a specific target hardware for the target board. In this case, we've got ROMs pre-arranged, and as soon as we get hold of the RZV2, we'll be able to give you a runtime for that. So there's different flavors. There's a G2L with software rendering and DRM, ones with hardware acceleration using the Wayland OpenGLES 2 drivers, and we can create these and optimize these for whichever platform we need. So this isn't all that we do. We have a great many more, but if we included every one of these in the install, it'd be gigantic. So we don't do that. And then I would literally click apply and run. And if I had a board connected, let's say it was a G2L board, that would deploy. It would copy the assets across all of these files, deploy those to the target as you specified, over SCP, which is a SSH connection, copy across the runtime, so deploy the runtime files that it needs to execute, and we run a kind of a script file that executes on the target, which sets up a couple of environment variables, and literally that's it. So one-click deploy, no cross-compiling, no complicated build environments. Okay, so that's what we do for a Linux target. I'm going to switch now to a slightly different application that I'm actually running on the RZ on the RA8 board rather. I'm going to close that and show you one that I prepared earlier. So this is the demo. This is a landscape version of the portrait we're showing on the board because it's easier to see in the demo window. But essentially, I can take this application. I'll show you it running here. This is running on our simulator. So this is a desktop version of the runtime. And you can see what it is. I'm on a very large 4K display here, but this is actually a native resolution of 480 by 854. So this is running on the target board, but simulated locally. So I'm running that on my Windows desktop version of the storyboard runtime. Okay, so what you can see here is there's basically trace output, and it's showing what's happening behind the scenes, and we can see some of the animation going on. It's very effective. The animation itself is quite simple in Storyboard. We have a timeline editor. What we're showing there is the startup animation. You can see that it's a bit like, and this is where Storyboard comes from. It's a bit like a video editing tool where you can synchronize everything. And we're showing animations as changes of parameters like the alpha or the hidden or the X and Y position to move something over time. Very straightforward, very simple to do. We've even got a simulator to test out the animation. So if I click that, and that's going to loop around. So this is a startup sequence that you saw on the screen, and you can see it, and you can use this to perfect the timing and move things around and get everything synchronized. Okay. So enough on the UI there. Let me show you about deploying it, in this case, to the MCU. I've prepared a kind of framework for this. So this is what we call an export configuration. And before I was exporting as a GAP file, which is a kind of a file system target. Here, most RTOS environments don't have a file system. So you could have something like FATFS, in which case you could send over the files. But in this case, we're going to be using something called Storyboard Virtual File System, SBVFS. So the virtual file system is a special kind of header file format that we've created. And essentially, you'll see it shortly. Essentially, this is a way of laying out and encoding all of those assets such that they get compiled in and located in sectors in your flash. So it's kind of a linear addressing using XIP or direct addressing mode to the flash. So we encode them, we deploy them as a header file, and that header file gets added to your project. So we've got the various aspects here, the model and such. So fonts in this case, there's some estimations here. You can see that the real-time resource estimation that Scott mentioned before is very useful. You can start planning here that you're not going to run out of space, and you can use this early on to specify the amount of hardware and software you're going to be deploying. Interesting here is maybe images. So PNGs are native compressed images. So what this means is that if we store them in native format in Flash, we then have to take them out of Flash, expand them or inflate them, and use intermediate buffers to kind of hold that image once it's been inflated. So you can see here that let's look at the tick glow here. In its compressed form, it takes up 41K of flash. This could be external flash, by the way, QSPI. But when we inflate it in memory, that is now expanded into a 550K of memory. So that's the memory buffer that we use to display that. When you add together all of the other images, we actually load and cache them so that you don't do this more than once unless you really have to. You can start to see that it uses lots of memory. And it's not particularly performant in terms of graphics acceleration. So this is where using a GPU and some of the ARM2D libraries come in. So we can start to use some of the graphics acceleration by switching from what we call native format to one of the direct formats. So let me think, RGB 565. So now what's happened is you'll notice a difference in the sizes. At design time, we've pre-processed that file. We've inflated it. We've laid it out in a way that is compatible with the target board and the GPU, such that it can be blitted or direct copied from flash directly to the frame buffer. So in this way, we remove the intermediate buffers, and we also remove you can see the memory and the RAM sizes drop significantly. We also remove the CPU cycles and the inflation kind of CPU cycles. So it's a very efficient way of doing things, and the ARM2D library does this for us. It's a very good way of leveraging the DMA engines and other hardware on the target board to offload the graphics processing. So most of the rendering operations are read, modify, write of pixels. So we're looking at regions and blitting and alpha blending. So this is a really good technique, and it's a really important way of getting more performance out of your target. Okay, so those choices are made. I'm going to switch that back. You can do that on individual image basis or at the top level. And what that does now is if I click run, I'm going to generate a header file. And this is basically the output from the storyboard world and the input to the code world. And so what that looks like is here, and I'm not going to spend too much time on that. But we have the model at the top, and at the very end, we have what we call a resources table. It's a very similar concept to maybe a file allocation table, but this is a lookup table for the resources in Flash. You can see the name of the file, the resource pointer, and also the size of it. So this is how we look up the images, and this is how it's stored. You can see they're all kind of hex encoded and stored as PNGs are stored in hex format. So this can be built and compiled. Okay. How are we doing for time? Okay, I'm going to be quick on this. So this is the Kyle MDK5 environment with the ARM Compiler 6. And what we've got here is the project with all of the storyboard libraries. You can see it's very, we call them plugins. These plugins are optional components which do certain features and drive certain elements of the UI. If you don't want to use them, so if you're not using gestures, you're not using gradients, you don't have to deploy those libraries. So these can be added or removed as necessary. So there's a whole bunch of those. You can see it's very componentized, so it's easy to reduce the footprint. And these are where the main engine libraries are. Okay, so those are delivered, pre-tested, pre-validated by us, and those are literally added as static libraries to your project. And essentially we have one file or two files if you include the model that we just copied. The entry file, this is basically the storyboard application. And I've already flashed this to the board. And what I'll do is just hit debug here. So I'm going to start that. Remember I told you we basically add a task. So this is pre-deployed. I'm going to run through the first couple of steps here. Essentially, this is all template code. This is BSP code from Renesas. This is generated for you with the various code generation tools, and you're adding storyboard on top of it. So you're kind of complementing the base. And if I hit go here, this is running the application, loading it, running it. At this point, I'll do a shortcut and show you my video, I think. Yeah. So this is the board. I'm going to hit run, and you should see that header file that I've deployed now running on the target board. So hopefully it's visible for you. Sorry, I kind of rushed the last bit, but it's basically very easy. Once you've done the design, once you've created it in storyboard, you're exporting it, you make changes, you re-export it, and you just rebuild the application. So we're not creating lots of code. It's mostly through the UI. There are some performance enhancements that we've included in the engine to use some of the hardware acceleration when available. And also we have the ability to add some local script files, some Lua or some JavaScript. Okay, so at that point, I'm going to stop and hand it back to Scott.
Thanks, Gary. That was a ton of useful stuff that you shared with everybody. Thank you very much for all that great information. All right, so just to kind of quickly kind of wrap things up before we kind of jump into your questions, definitely, what makes Storyboard different from others in the market? As we kind of touched upon, it offers powerful GUI development with the benefits of low code. So instead of having to code everything from scratch, like you saw Gary do, like action events, you can add via clicks rather than code. It has that distinct separation in design and code environments, with the front end design being decoupled from the back end logic, really enabling you to work closely with designers to create exceptional UIs. The rapid design and iteration and re-import technology really allows you to import from initially Photoshop, Sketch, or Figma files, and then re-import any change design files. And then, of course, we have those pre-built optimized runtimes that are ready for you out of the box for all the different Renaissance hardware that you're looking to support. So if you'd like to try it out for yourself, we do offer a full-featured free trial of Storyboard. It can be found on our website, which is cranksoftware.com, and you'll see it under the free trial button. Also, we have a free ebook that you can access that provides tips and tricks for developing your next killer UI, which can be found under our Learn and Resources section of our website as well. So with that being said, let's jump into the questions that you have. All right, let me take a look here. Let me open it up. All right. All right, so the first question I have is for TJ. TJ, are all the products mentioned in the webinar today available?
Yes, thanks, Scott. Yes, yeah, all the products are NPIs, we call them, new product introduction. They're actually all in full production.
Perfect, thank you. The next one actually kind of goes along with that, and I can answer this one. It says, which Renaissance platforms does Crank have runtimes for? And so definitely when it comes to the MCU side of things, which is the RA family, we have runtimes for the RA6M3 as well as the RA8D1. When it comes to the RZ family, we have runtimes for the RZ-A1H as well as the A1L, and we're currently working on one for the A2M. When it comes to the RZG, we have it for the G1M, the G2E, and the G2M and G2L series. And when it comes to the RZV, which TJ talked about, we just released, completed one for the RZV2H, which is their latest within the Vision AI side of things. Next question I have back to you, TJ, is where can I get more information on the helium vector extension set architecture for the RA8D1?
Okay, yeah, that's a good one. Yeah, I have a slide that'll be included in the deck that goes in more depth on about helium vector extension, and so that that'll come out after the webinar recording is available. And also, of course, you can contact your local Renaissance sales people, sales FAEs, and marketing/business development like me.
Perfect, thank you. Next question is, if Storyboard is decoupled, how does the Storyboard application control code link up with my application and tasks? Gary, I think this one might be for you.
Yeah, so I mentioned it briefly. It's something called Storyboard.io, and essentially it's a queue between what we call the back end and the front end. So you're sending and receiving events which trigger actions. And so we have an API for that. It's called Storyboard.io API, and it's very simple to use. In an inter-process environment on Linux, for example, it's something similar to a POSIX API, open, close, read, write. On RTOS, it's more like a FreeRTOS queue object. But there's a simple API, very, very flexible. And it's important to keep the front end and the back end abstracted where possible. It allows you to test it and develop it independently.
Perfect. I have another one, Gary, if you want to keep my going. It says, what is involved with porting Crank software to other target platforms?
So essentially, it's down to the core. If you think of the various components, there's There's a runtime specific to the core, so Cortex M7, M33, M4, or whatever. The RTOS, so the kind of API for the system, and also whether it has any graphics acceleration or not. On top of that, there's we compile it with a toolchain, GCC or Kyle or IAR. So we have an automated CI build environment, and with containerized, we can spin some of these things up very quickly. Chances are we've probably already got a runtime. So just reach out to Scott or myself, and we'll be able to give you some more details.
And another one, you spoke about using Photoshop to create the UI. Do I need to use a design tool with Storyboard?
No, I don't personally. You can easily drag and drop. So we have what we call render extensions. These are the primitives. So you drag a text box. We've also got something called components, which are kind of pre-built objects, things like buttons and sliders and text boxes and things like this. So you can drag and drop those. And you can just literally drop PNGs or GIFs or JPEGs in as well and move those around the screen as you need.
Yeah, so just to build upon that a little bit, yeah, so as Gary mentioned, you can easily build it from scratch. You can import all your individual assets and build it from scratch and all that. But just what we do by interacting with design tools and having that direct integration to design tools just really helps kind of speed things up for you. And especially, if you're in an industry where the UI is vital to help your product stand apart, right? Some industries, it's more important, things like consumer goods. Wearable markets, etc. That really kind of working with a design firm or maybe a design person in-house, a design team really makes it easier and speeds things up. But definitely you can always build up an application the good old-fashioned way as well from the ground up. So. And with that being said, I believe that is the last question. So I just want to thank everybody for sticking around and all, because we had a lot of great things to do. We did go over today. We will share this with you within the next 24 to 48 hours. So thank you once again for taking time, like I said, out of your busy day to come listen to us talk about all the great hardware that Renesas has to offer, and then how we can make your GUI development a little bit more efficient and faster for you. That being said, have yourself a great day. We'll see you on the next webinar. Thanks.